Hello. Hopefully you're still awake, even without the coffee. My name is Guennadi Riguer. I'm with AMD, where I'm a software architect working primarily on making VR solutions. So today I want to talk about the temporal foveated rendering, particularly for the VR. This is one of the rendering techniques, and it is inspired by the fact that we want to optimize performance. Optimizations and performance optimizations in particular are very dear to my heart. And our R&D guys have been very busy trying to cook up some of the interesting techniques. And that's one of the techniques that I want to talk about. So today we'll start by talking a little about the motivation, why we want to do this. Certainly performance is one of the aspects. I want to also review some of the other techniques that sort of have inspired or coexisted with our development. Then we'll talk about the technique itself. And I also want to bring in another aspect, which has been talked about by Michael Abrush, by Carmack, and that's the eye tracking. What do we do with the foveated rendering once the eye tracking comes in a play? And hopefully, if we are to believe Abrush's predictions, that's within the reach, within, I guess, 4 years. Let's start with understanding why we're trying to do this. So it's been discussed ad nauseum that we need to render almost twice the amount of pixels just for the lens matching. And the reason for that is the distortion that is applied by the compositor to compensate for the distortion in the HMD optics. So in the end, you start with the linear image that is larger in size. Through a couple of distortions, you still end up with a linear image at the end. But having almost twice the amount of pixels that you need to render, that's kind of wasteful. And there are many techniques that have been discussed. In particular, there are a couple that are similar in spirit in terms of the pixel reduction that I would like to highlight. But there are many more that focus on lens matching or fixed foveated rendering that have been covered by our competitors, by many other parties involved. So two in particular where they rely on stencil rejection are radial masking that was talked about at GDC a couple of years ago by Alex Vlachos from Valve. And the other one was talked about this GDC by Simon Hall, where they've used it for PSVR optimizations, and it's called resolution gradient. So I encourage you to go out and check out those presentations at the links provided if you haven't seen those. And there are many more optimizations that can be done through various lens matching techniques. Certainly, I'm not going to have time to go over all of those and compare. So we'll skip that for a much longer talk, and you want to catch me after this talk, we can talk about those. The one I want to talk about is the new technique that we're proposing that we call temporal foveated rendering. It's a hardware-independent software solution, which means that it'll run on a variety of hardware from multiple vendors. It doesn't rely on any specific API or hardware features. Good for all hardware, old and new. The solution that we're proposing today, it's a decent solution for lens matching, and it's a perfect match for foveated rendering once the eye tracking comes to play. So the idea is actually quite simple. What we want to do is to reduce number of pixels on a periphery frame to frame by rejecting some pixels. And we would use either a quad-based rejection or per-sample rejection with stencil or depth. And I'll talk more about those things. And then at the end, you still want to have full cohesive image. You don't want to have holes in your image. So we reprocess the skipped pixels and fill those holes using the pixels from the previous frame through certain reprojection technique. Let's start with the bird's eye view of the pipeline. The rendering pipeline is actually quite simple. We start with rendering a depth, which is a full resolution depth. And it could be combined with your just normal depth prepass. So you render the depth. That depth, along with some other things, could be used for mask generation. And that mask could be set up within a stencil or depth buffer. Then we use this stencil or depth mask to actually render the scene. So the white pixels, white blocks in the mask represent the pixel blocks that would be rendered on a current frame, and the black ones would be rejected. And same thing with the rendered content. The black areas represent the blocks of pixels that would not be rendered, that would be masked out with a mask. And then the last step is basically taking a previous frame, reprojecting it, and combining it with the current wholly frame based on the mask. So the darker pixels or darker blocks of the final image represent the pixels reprojected from the previous frame, versus the lighter ones are from the current frame. So these are not necessarily to represent the color variance from the frame, but really showcase the source of the pixel, current or previous frame. So let's drill down into this pipeline. Depth rendering is pretty simple, so there's probably no reason to talk about that. It's pretty straightforward. So let's jump straight into the mask generation. What we do, we set up a quad-based rejection using either stencil or depth. And depending on whether stencil is fully used by the application, we might want to use depth. Or if stencil is available, or even a couple of bits, maybe even a single bit, we can leverage stencil in that case. We need to do a quad-based rejection because this is how GPUs work. The GPUs do not work on individual pixels. They process 2 by 2 quads of pixels at a time. So what we would want to do to make those 4 pixels within a quad coherent so they can be either fully rendered or fully rejected. Otherwise, if you just reject a single pixel, knocking them out individually, you would not get the performance benefit that you would expect. Alternatively, we could also mask out using per sample rejection with MSAA. Effectively, if we use MSAA as a sort of a super sampling solution with a custom sample patterns. However, even though it has much smaller holes, it has its own set of trade-offs. So both methods are quite valid depending on what you're trying to do. The mask is set up based on several criteria. The simplest one, I guess, would be the radial masking, similar to what other methods have done. And this is just based on the distance from the optical center of lens or foveal region. And also we add some additional heuristics where we detect some high contrast areas or edges, as well as occlusion, reveal, and so forth detection. All these factors are combined using some mathematical function, and they're used to modulate the interlace pattern generation within a mask. So let me walk you through what the mask would look like for each of those various things. So let's start with very simple radial-based masking. This is, again, somewhat similar to what you would see in other techniques. However, the interesting thing is that you would see a much more gradation than you would see in other methods. In particular, for radial masking from Valve, there's only 2 states. There's either full image render rate or checkerboard pattern on the outer ring that is reduced with the mask. There are more gradations or steps in Simon Hall's method, and we take it a step or a couple of steps further. So this is actually pretty straightforward. As far as the mask goes, the middle region, the white, that's fully rendered, and then any other black regions these are the pixels or quads of pixels that get rejected during rendering. Now, if I look at the next frame, you'll see that mask changes. Let me quickly flip back and forth. So you can see that the mask changes. And this is just 2 consecutive frames. There's a much longer sequence of frames. In this particular case, we've played with several durations of sequences. In this particular case, and you can probably count it based on the rings, that we use 16 frames. We've also played with frame sequences of 9 frames and some others. You might say, well, 16 frames, that's a very long time. That really means that every pixel gets re-rendered within the 16 frames. And the pattern is done in such a way that it's a pseudo-random, changing frame to frame in such a way that pixels do get re-rendered, in the worst case, within the 16 frames. Now, I'll show some of the masks that depend on the content. Edges, in particular, would be content-based. So this is roughly the scene that we would try to render. And this is based on the Unreal Engine content. We've played with a number of different scenes with different content there. I just picked one, and hopefully it's not too dark to see. Basically, all the other images will try to mimic this. I haven't tried to make all the images pixel aligned perfectly. So you might see images shift a little bit, but this is roughly the image that we are trying to generate. Once we add edge detection, which is based on the color from the previous frame, we've marked some additional pixels. And there are several reasons why we want to mark the edges or highly noisy regions. For one, these are the areas where we might have trouble reprojecting them perfectly, when there's a little bit less variance in color, and we do apply some additional things on top of it to make it less noticeable in terms of the ghosting. But marking pixels, specific pixels that are on the edges or in the high contrast areas, that makes first image quality much better. The other thing, once we start talking about the foveated rendering with the eye tracking, this is also a very important factor because we try to do the edge preservation. The other component that we add to the mask is occlusion reveal. Basically, as you move, and this is exaggerated example just to highlight that many more pixels could come in, but generally not that many come in view. This is really kind of boosted effect to show that more pixels are effectively added. But as the frame moves, or as you move, and black regions or the unmasked regions on the periphery of the frame, on the edges, would show up, we would have no information in the previous frame to reproject the pixels from. So those would need to be marked, as well as we detect depth-based effects of parallax, where if something moved too far, we would not be able to reproject. All these streaks would really show up, particularly when we reproject frame to frame, and it could take up to 16 full frames to re-render the image. We want to make sure that the pixels are as correct in the first place as they can be. So we add all these additional pixels, but not as many as you see here in the exaggerated example. Once we set up the mask with a stencil or depth, then we render this scene. The mask generally could be just a single stencil bit. However, we could also hijack some additional bits that we would mark on the step when we do the scene rendering. So generally, the scene rendering would be done with the mask, and we would apply the savings for all these pixels that is your normal opaque geometry, saving on the complex processing for your expensive light interactions, all the expensive materials. Transparency, all these transparent objects, they come up as an interesting challenge. And there are several methods that we've played with as to how do we deal with translucency. In some methods, we've tried to render into the same target. We could render translucency separately, either with or without mask, or maybe even taking translucency to a lower resolution, let's say like a half resolution target, which could also have a certain mask applied, which is coherent with the other mask that applies to solid geometry. Also, when we render a scene, we want to render high-quality velocity vectors. Those could be used for some of the post-processing steps. Or we could rely on velocity vectors that are separately rendered out specifically for reconstruction and for the edge detection. So this is, actually, it's a little bit too dark here, but hopefully as the presentation gets posted, you can see it in a better detail. This is what a masked scene would look like. Right in the middle, you see pretty much all the pixels rendered that provides a high fidelity for your most important parts of the scene. In case of lens matching, this would be the center, the optical center. And this is where you want to have as much details. On the periphery, as the image is going to get squeezed, and because of the optics that are not perfect on the periphery, you're not going to notice as much details. So we don't render as many pixels, of course, because of the mask. And this is the same or similar scene in a headset with the mask applied. Again, because of the warp, even a larger portion of the lens-matched image is fully re-rendered, and the peripheral regions that are squeezed by the warp, they contribute to fewer pixels in a visual field. And then we come to the frame reconstruction step. So what we want to do at this step is to fill the holes that are present in the frame. And this would be the step where we reconstruct a full-size image. Generally, that would be done prior to applying post-processing passes. However, some post-processing might actually be combined with this frame reconstruction. In a spirit, this is somewhat similar to the temporal anti-aliasing. And actually, we could combine, if application is relying on temporal anti-aliasing, we can combine the TFR with TAA as well. The important part, besides the reprojection from the last frame, is that we perform some advanced color clamping based on the valid pixels in a new frame. And the reason we want to do this, because if we just reproject pixels from a previous frame in a very dumb way, you can end up with those streaky pixels that leak from the previous frames. And because of long sequence, we might end up with long trails of those pixels that get wiped out only within the 16 frames. And this is particularly well noticed here in this synthetic scene where you have very high contrast, solid colors. It might not be as noticeable in more noisy scenes, but this is a perfect example to showcase where neighborhood clamping provides horrific, or lack of neighborhood clamping provides potentially horrific results. This is the same scene with wide range of motions, pretty much the same conditions with the neighborhood clamping applied. You can see that it's pretty much eliminating all of those streaky pixels. There might be a couple runaway pixels just on the edge, but that would be eliminated within a frame or two anyway. So far, we talked about lens-matched solutions. And the most interesting part is applying this foveated rendering approach with the eye tracking. So with the eye tracking, as discussed by Michael Abrush and others, you would have ability to figure out where the gaze direction is very, very quickly. So we can adapt the rendering to the eye tracking and try to create an image that matches perceptually better to what our eyes are able to, and the brain able to consume. So in the simplest case, you can think of it as we take this radial mask and we move it around based on the gaze direction. So let's talk about this foveated rendering with eye tracking in general. In theory, and many think that it should be simple, right? Basic theory is that only a small part of the visual field, the fovea, is perfectly sharp. And there is a very sharp fall-off of acuity from that to the end of the visual field. Since the fovea can be tracked, and it can be fairly accurately tracked within a couple of degrees within a frame, then all we need to render, and again, this is just a theory, that we need to render perfectly sharp image only where we're looking. So it can be done, and this is sort of a conceptual image of what it would look like. The problem is that reducing the quality on the periphery, just like image shows, does not produce very good perceptual quality. Reality is that our human vision system is quite complex, and it deserves a talk on its own, but it'll suffice to say that you just cannot reduce the resolution on the periphery. The rendering needs to preserve certain features on the periphery. It needs to preserve edges, it needs to preserve contrast, feature size, and so forth. And also, render needs to provide some temporal stability. The other interesting thing that we cannot reduce the overall frame rate. However, we can stochastically reduce update rate on a periphery. This would amount to a really good eye-tracked foveated solution. And the fact that we're actually doing this pseudo-stochastic update on the periphery within the technique we are discussing, temporal foveated rendering, this actually provides a very good match. So because of edge, feature, and contrast preservation, because of pseudo-random stochastic distribution of pixels on a periphery frame to frame, we actually have a very good perceptual match for the eye tracking. And we've played with the technique in the eye-tracked headsets. It actually gives us very promising results. On the base passes, we are able to achieve maybe 2 to 4 times the pixel reduction in the headset. And of course, the technique would work with the desktop eye trackers as well. We've played with those. It seems like it's a very promising technique for various sets of scenarios we want to target. Last but not least, I'd like to offer a big thanks to my colleagues who worked on conception as well as refinement of this technique and all these various prototypes to figure out various trade-offs. That's as much as I have for today, given that this is a very short talk. Thank you for your attention, and just to keep lawyers happy, I'll flash the legal notice there as well. Thank you.